Hello, everyone. Welcome to another ACE Spotlight event. I'm Shahrzad Hosseini, a data scientist at Biosymmetrics, and also machine learning and materials stream owner at ACE. ACE is a global community of machine learning researcher and practitioner, which has the aim of bringing the cutting-edge research in machine learning to a public and to a wide range of audiences through a wide range of ways. One is through creating a repo of recent papers that are coming out, and another is workshops that are happening regularly. For more information, please go to our website at ai.science or check our YouTube channel for previous talks and events. Today, I'm glad to have Zhenpeng with me. He's a computational material scientist at Department of Chemistry and Chemical Biology at Harvard University and Department of Chemistry and Computer Science at University of Toronto. He conducts research focusing on lithium-ion batteries and metal organic frameworks through different ways, density functional theory calculations, Monte Carlo simulations, machine learning, and high throughput computations to design materials with the interesting properties for different applications. Today, he's going to talk about his recent paper on inverse design of nanoporous crystalline reticular materials with deep generative models. Reticular frameworks are interesting because they have building blocks that give them a wide range of capabilities in terms of linking to each other. So that makes the design space very big and computationally costly if we want to do it through a traditional way of computation. So in this paper, he's going to show us how the way that they are proposing, which is variational autoencoder, can generate new structures. Without further delay, I give the stage to Zhenpeng. Please go ahead.
Okay, sure. Morning, guys. It's more than a pleasure to have a chance to present to you guys on our recent work. As introduced, I'm Zhenpeng, and I currently work for both Harvard University and the University of Toronto. And today I'm going to introduce you guys for our recent work on the inverse design of nanoporous crystalline materials with deep generative models. And as many of you guys you may know, like the 21st century is supposed to be the so-called renewable century. Like people have been trying so hard to transferring from the traditional primary energy resources to renewable energy resources, such as solar and wind energies, and many aspects of the so-called renewable economy, from its utilization or generation, to its storage, to its utilization, to its emission reduction, are actually closely related to the discovery and design of new material systems, such as for energy conversion or generation. We would like to have like a high efficiency photovoltaics, thermoelectrics, and so on. And for energy storage, you get all like batteries or supercapacitors with even higher energy density or capacity. And for energy utilization, you would have higher performance semiconductors and even lightweight alloys. And for the very special emission reduction part, you would have super gas absorbents, membranes, catalysts, and so much more. So a clean and sustainable future actually demands high performance and low cost materials. And with that in mind, what's the state-of-art materials discovery paradigm looks like? As you can see from figure at the left side, like the currently design process of new type of materials actually goes through several steps. And firstly, you would have an idea like what kind of composition may bring you better performance for certain applications. Such from the viewpoint, from the so-called either chemical intuition or educated intuition, like you think certain kind of metal or transition metal combination may be good. Then you have that in mind, and then you trying to then you go to your lab and try to synthesize it, and then you put all the powders you obtained in and building a device based on that, and then you put the device into test and characterization. And if you are lucky, the whole procedure can take several weeks to finish, and you are getting what you want. But for most of the time, you are not. People are not so lucky, so you have to start over again and try more and more different systems. But it has been known, like the chemical design space for the discovery of a new material system is insanely large. It's on the level of 10 to the 60. And as a fair composition, like there are only 10 to the 24 stars in the observable universe. So it's insanely huge number. And the manually explorable space, chemical space, is only approaching level 10 to the 6. So there's a huge gap in between. So how can we actually make this gap, close this kind of gap? This kind of closing this gap actually calls for a more efficient way to explore the near infinite chemical space. And the people have been developed several different ways to actually accelerate this kind of procedures. Well, with the first idea in mind is like people think about why we cannot like do studies or investigations in a parallel way. Like instead of trying to test and synthesize system one by one, we can do either computational or experimental study in parallel for several thousand different systems. With that kind of a capability, people now can explore like a slightly larger chemical space. This is so-called high-throughput screening method, and with the metro and development of machine learning models, people now have the capability to predict properties for untested material systems. And with these so-called discriminative models, people can actually save part of their computational and experimental resources on those systems, and at the same time, they have enhanced capability to explore even larger chemical space. And this idea is so-called high-throughput virtual screening. And what about if even the chemists or the material scientists don't know which way to go to have materials with better performance? And what should they do? Actually, people has been using this kind of so-called generative models, which has been getting more and more popular and stronger and promising in the machine learning field. This kind of model not necessarily predicting properties for new systems, but it can actually model the system itself, which means it's if well trained, it can help you to develop or design new systems. And combined with the discriminative models, now you have a way to automatically generate systems and following the trend of the property gradients. Now you have the automated way to significantly accelerate the material discovery process, and it is so-called automated virtual screening method. Oh, okay. Right now, right? Okay. No problem. Sorry, I didn't actually realize that. Sorry. Okay. So in today's talk, I would give you guys a demonstration, like how the material scientist has been using this so-called automated virtual screening method to solve very complex materials design problems. And the system we are dealing with is so-called reticular frameworks. And if you can take a look at the structures on the right side, you can see the reticular frameworks, which is on the top. It looks quite different with normal materials, such as the oxides on the on the right bottom corner. Like it has a pretty high surface areas, and it have large voids and large pores in the structure, which means both gas or liquid molecules can go in and stay there, and may have some chemical reactions with the with the branches and the nodes, and gets out. And what is more amazing is like the pore is actually tunable. You can have a way to make it bigger or smaller, and also the internal surface properties are actually adjustable. So with all those amazing features, the reticular frameworks such as metal organic frameworks or morphs, or covalent organic frameworks or curves have demonstrated so many applications, from gas storage to gas separation and storage, sensing to catalysts, ion conduction, biomedicine, and so much more. And how people actually synthesize or design different kinds of reticular frameworks. Actually, you can understand the structure as a Lego building blocks. You can see you can see from the example here, we have arm of 1. It actually can be decomposed into different modulars, such as nodes. Here we have zinc oxide here, and linkers, like one benzene ring linker, and the way how they would self-assembled to form a structure, which is called topologies. Here we have a PCU here. And what's more important is like, if you have like a replaceable linkers, such as linkers with different number of benzene rings, or even more complex, now you can have a way to synthesize different types of frameworks with different sizes of voids and pores in the structure, and they would lead you to different kind of chemical and physical properties. And at the same time, not only the linkers can be changed, the nodes can be tunable, the topology or the geometrical way for them to synthesize can be different. And then with different node sets, linker set, topology set, you have a way to synthesize or discover new frameworks with different structures and distinct physical and chemical properties, just like what I shown here as examples on the right side. And and currently the node set have the size of around several hundreds, and however the potential linkers are nearly have the same size of the whole chemical space, because nearly all kinds of molecules can be used to build this kind of structure. So they would nearly have the same size of the whole molecule or the whole chemical space. And the available topology known so far is also on the level of several hundreds. And if you can do combinations between all those different modulars, and by a simple multiplication, you would realize you would have a chemical space nearly infinite. That's both good and bad. It's good because now you have a significantly expanded scope of useful materials for future applications. It's challenging because all previous materials design method now becomes so insufficient, because chemical space is exceedingly large. It's so much larger than any kind of materials families people have been working with. So then it calls for the so-called property-oriented automated materials design approach. And we
excuse me, Zhenpeng. If I could stop you here, could you just summarize here? So your work compared to computational, high throughput computations, just to give a cons and pros here for audiences to be able to follow up the work.
Yeah, sure. Actually, let me go back. Just like what I said, the high throughput screening works are the very first step or people on the road, people trying to accelerate the whole design procedures or the whole design paradigm. We also did some high throughput screening too. It's basically the basis of the whole paradigm. And the problems, not the problems, the limitations for high throughput screening is its scope is still sort of limited, because you know what kind of linkers you are using, and you know what kind of topology that you are using, and you know what kind of nodes you are using, and you are still limited to certain types of reticular frameworks. But with deep general models, you can not only using all the known linkers people have been trying to synthesize and test, but you can design new linkers, which means you can explore even larger or significantly larger chemical space or chemical design space for new types of frameworks. This kind of size difference or space difference is the main difference between our method to the traditional high throughput method. High throughput method is not outdated at all. It's just the base for many more more advanced methods to be used to help the design of new frameworks.
Yeah, but we should also bear in mind that whatever is also designed through generative models needs to be approved through one sort of an experimental technique to know that design is valid or not. Yeah.
Yes, that's always true. That's always true. Not only for high throughput virtual screening or high throughput virtual screening or automated virtual screening, we always need validations. That's always true. Yeah, that's yeah.
Thanks.
No problem. Okay, let's move on and take a little bit step back. What is a general model, generative learning, and how it can help to solve the problem? And it's actually the availability of the massive amount of data, boosted the development of machine learning techniques, and the deep neural networks.
Excuse me, sorry to interrupt you again. Would you mind holding your microphone on your hand? It's still rubbing and making some background noise, which is making difficult to hear your voice, if it's possible at all. Thank you.
Actually,
or secure it in a place so it doesn't rub to your shirt or something.
I'm using the correct microphone. It's kind of
you're using it correctly, but it seems that it's rubbing to your shirt or a desk or something like that. It's making some background noises.
Okay, how about now?
That's much better. Thank you.
Yeah, I'm holding it. I will holding it all the way.
Thank you so much.
No problem with that. Okay. Okay, actually, the deep neural network-based reinforcement learning has been keep beating people or humankind on either the enormous search space yet well-defined game like Go, or the real-world level complex multi-agent challenge such as StarCraft. And usually, when people talk about the machine learning models, especially their applications into practical problems, usually there are two types of models comes out. With one type is the so-called predictive machine learning algorithms, which means giving a data point X, it can help you to predicting a property Y after proper training. And another type of machine learning models are generative machine learning models, such as the generative adversarial networks or GANs, or the variational autoencoders. They are not necessarily deal with predicting a property Y, but they are modeling the data itself. A very famous case study is the people who train their GAN model with 200,000 image for celebrities, and the GAN would able to giving out those kind of images for those kind of so-called imaginary celebrities. And you can see from these pictures, it looks really, really familiar to your eyes, but you just have trouble to recognize who they are because they are not real people. They are just fake images generated by a random number generator. That would be pretty promising because that means the general model can actually learn the internal connection between the outlook and the celebrity. It's actually understanding what a celebrity would look like. And if we can put that into use, maybe the general model can also learn chemical rules, or the connection between a chemical structure and its properties. And it can also help us to make predictions. Have that in mind when people are starting to deal with the predicting in or put the general modeling, general learning into the application of chemistry. The first problem they run into is the representations. You can see molecules are usually looks quite different from like the beautiful faces. So we have to come up with one way to really represent them. And it's fortunate for molecules because people have been devoting their time for several decades into this specific research direction. Like people already have some way to represent represent molecules such as smells. Smells is basically a string contains all the atoms in molecules and all their ways to bonding to each other. And it's kind of a very convenient tool in hand. The pioneer in our field, who is Raffel, actually come out with this so-called sequential variation autoencoder. Using this autoencoder, they actually treat the strings like languages, and they use the variant autoencoder to learning the chemical rules or the chemistry of building like reasonable chemical molecules as grammar. And with the grammars learned, now the chemical version of autoencoder can be by itself generate new sentences, and these sentences can be meaningful molecules at the end. So can we actually apply this method to the design of new types of reticular frameworks? The first problem we have to deal with is still the representations, because the reticular frameworks are insanely large. Usually they contain several hundred to several thousand or tens of thousands of atoms, and it's a 3D crystal, not like 3D crystals, and it's periodic in space, not like the molecules, which are usually not periodical in space. And it have really complex topologies, such as you can see from the MOF 117. The way it can connect to each other for all the molecules in the structure is really complex, even by seeing. So it would be challenging to find a compact, accurate way to represent the structure, and we need some simplifications to do that, to realize that. And if we go back to the way people trying to synthesize or design the reticular frameworks, you can see there are different types of molecular modelers, such as nodes, linkers, and topology, and they actually have different types of chemical varieties and different amount of chemical varieties. Such as for nodes and topologies, they are usually at the level of several hundreds, and they are actually confined by the available of nodes people can synthesize and can put into use. However, at the same time, the size of the potential linkers are much larger compared with the size of node size and topology size. So how about we treat the nodes and topologies as categories, and we treat the potential linkers in a more chemical, meaningful way. So then we come out with this kind of reticular framework codes or RF code. Like we have the nodes and topologies, one hot encoded, and we have the linkers represent using more chemical meaningful way, such as graphs. Now we come out with one way, which is canonical, which means one reticular frameworks only have one way, only have one RF code, and it's invertible. It can be transferred forward and backward from a morph structure and the code. And it's also compact because we decompose the structure into their building blocks instead of reprint all the atoms one by one in the structure. So it's the time to release the power of deep generative models and put them into use. We were able to design this kind of automated reticular framework discovery platform, which is empowered by a supramolecular variational autoencoder. And the autoencoder is a multiple component switch on and off semi-supervised variational autoencoder. And as you can see from the structure, which can be developed into, it can be divided into three groups or three major parts. The project is also proceed in a three steps way. Like the first step would be like the reticular frameworks identification. In this step, we would build the RF training pool from all known framework structures. And then we would do the frameworks prediction. We train the supramolecular variational autoencoder and predict valid new framework structures. And then we do optimizations, and for specific applications, we search for frameworks with top properties. And as a starting point, we use a computational-ready experimental morph database, which contains around 14,000 reticular frameworks. And we break them into their building blocks, and we identify them by finding and locating their RF codes. And also we do some recombination between all those building blocks and coming out with new morph structures. And by the end of the day, we have a training pool which contains around 2 million RF reticular frameworks in the training pool. And we would train our model with all those 2 million frameworks. And for part of them, which around several thousand, we calculate their properties, and we would like to use those properties for the training or for the design of new frameworks with improved properties. And at the same time, we actually were able to do some fragmentation analysis for all the building blocks, all the linkers currently used by all the reticular frameworks. And the inner circle would stand for all the basic bricks people have been using in building different frameworks. You can see how people have been putting them into use by gradually add 1 or 2 more bricks to make real linkers. We call it like the linker scaffold tree, which is shown here in the figure. And after training the model with all the training pool, we were able to build. Now we were able to actually explore the geometry or symmetric connections between different types of frameworks. The first demonstration we do here is like we start with one known reticular frameworks, and we were able to sampling its neighbors in the lattice space. You can see here we start from NU1104, and we sampling its neighboring points in the lattice space, and you can see with different amount of distance, you can see how the structures gradually evolves into different shapes and different topologies, and with different nodes and linkers too. And also we now have the capability to explore the underlying connections between two very different geometrically very different structures, such as here the NU1104, which has a cubic structure, and here the NU1000, which have the hexagonal structure. Now we can have an understanding of how those kind of structures can actually have a connection between them in the lattice space or in the design space, like how you can gradually change the linkers, nodes, and topologies, and realize this kind of a transition from one structure to the other. And afterwards, we would train our model with also properties. Now we can realize this kind of optimization using the supermolecular version of autoencoder. Here we use one property as an example, which is carbon dioxide and methane separation, which is carbon dioxide uptake. Like you always want like a higher carbon dioxide uptake for your gas absorbance when you try to separate them from the mixture. The first step we want to demonstrate is so-called ISO reticular framework design, which has been used by reticular framework experimentalists. Like people actually constrain the topologies or constrain the way building blocks has like being like self-assembled to achieve a framework. Here you can see we stay with this FTW topology, and we start with one known framework, which is NU1104, and we gradually we keep the topology the same and gradually change the linkers. And you can see we were able to gradually realizing higher and higher carbon dioxide uptake from 0.6 to 1.9 to 2.5 to 2.9 to 3.8 to 4.3, and it's probably already close to the upper limit for FTW structure to absorb carbon dioxide. And in the second optimization, we didn't give our model any kind of limitations. We let it to take over, and we call it the global optimization. Now both the linkers, nodes, and topologies can be changed upon the optimization process. You can see we start from another like a known framework, which is the so-called LRMF1, which have uptake of port 2.8. And by changing different linkers and nodes and topology, you can see we were able to achieving the value to be 3.6, to be 0.8, to be 4.6, to be further to 6, and finally to 7.55. And it's already very close to the record holder to the gas separation applications. And you can see we were able to identify a bunch of different new reticular frameworks which have superior properties. And as an example, here we're still using carbon dioxide uptake. You can see our top candidates are really strong competitors, even compared to the current record holder in the gas separation applications. And we are now waiting for further next step experimental validations, as also asked by Shahrzad several minutes ago. And to summary, we have an automated nanoporous maturity discovery platform for this kind of property-oriented inverse design, and it's actually the first effective approach to explore such a huge near infinite chemical space. And our model also like exhibits high fidelity in capturing structure features and predicting new frameworks for improved properties. And we were able to identify several top candidates for exemplified applications and waiting for experimental validations. And this platform can actually be applied to a much broader range of materials from covalent organic frameworks to metal organic polyhedra, hydrogen bonded organic frameworks, and so much more, and also for different applications such as drug delivery, electrical conduction, and so on. And last time, I would like to say thanks to all my collaborators, both here in University of Toronto and in Harvard, such as people from University of Toronto, people from Northwestern, people from Oregon, MIT, University of Waterloo, University of Minnesota, Google, Alberta, and so much more. And at last, I would thank all you guys for your attention. And it has been a pleasure to present to you guys. Thank you.
Thank you so much. Few questions before going to a question from audiences. Could you a bit elaborate on the techniques that you use to reduce the size of your graph when you're talking about? So it was a huge space size of the graph that you're using some reduction techniques to increase decrease the size. Could you a bit elaborate on that part?
Yeah, sure. I mean, the structure is large, so that means if you reprint the whole structure with graphs, that would give you really large graphs with like several thousand nodes. So what we did is we actually decompose those structures into their building blocks, which means we can save in our energy on reprinting the nodes, all the nodes with graphs, or also for all the linkers with graphs like repeatedly. We avoided to do that, and that saves us a lot of memories and size when we representing the frameworks. Such as here for the RM of 1, instead of reprinting all the items in the structure with graphs, we were able to focus on reprinting only the chemical meaningful linkers with graphs. And for the nodes and topologies, we reprint them as one-hot encodes. And that saves us a lot of memory space and making our code like much smaller, but still what is important, like it is still chemical meaningful and still can be used to predict new frameworks. That's what we want, and that's what we needed. Yeah.
So it's basically equivalent to using unit cell in other crystalline solid state materials. Like you have units of blocks of molecules, and you're using it as your nodes instead of using separate atoms.
That's an excellent example. That's actually an excellent way to understand that. But we actually even go further, because the unit cell of reticular frameworks is the reticular frameworks have several thousand items. It's already the unit cell for the MOF 117. So we have to go further and make further decompositions. That's what we have for the RF code here.
If you want to compare your techniques with selfies, how do you compare RF code to selfies representations?
Well, yeah, I know. Mario has given one presentation in this seminar, and we are collaborators. So those are selfies, and I assume you guys already heard that, so I didn't go to any details of selfies.
No, just to compare your representation with selfies.
You can understand our representation as selfie-based. We represent the linkers or the chemical interesting part with selfies, and all the other like building blocks with one-hot encode. It's based on selfies. We are actually using selfies.
Sure.
Yeah.
Yeah. Any question, Rouzbeh? I know that you have several.
Yeah, sure. Thank you so much, Zhenpeng.
No problem.
I have a couple of questions. First, page 7. This is just general chemistry question.
Yeah,
So
sure.
one of the applications that you have here is catalysis. Just for my better understanding, you have metal organic frameworks, and part of that structure is organic. And the suggestion here is to do redox catalysis. Do you think, just so that I understand this better, do you think these structures are stable under redox conditions?
It's a brilliant question. It's a brilliant question. And it's really on point. Like you have the metals which behave like the active centers in the structure, and upon like redox reactions, it will change the valence. Usually, when it changes the valence, it will also change the coordinations. So when they change the coordinations, usually the structure would lose some bonding and becomes, collapsed. And that's why people have been trying to looking for or searching for frameworks which are not decompose or collapse upon the catalyst reactions. That's actually one very promising research direction in the field. Like how can we actually develop frameworks like won't decompose or collapse upon redox reactions? That's very promising real research directions, and that's a very interesting question too. And what I know, most of the structures may collapse upon several cycles of redox reactions or catalyst reactions, but there are still some of them survived. Some metals won't actually change the coordinations upon changing valence, so it can stay there. And I guess the problem is like there are like actually not enough frameworks to realize that. So people are still want to digging for more in that specific direction.
So in real life application, will these behave better in the recycling cycles than, let's say, just simply inorganic catalysts? I'm trying to understand why we would use these structures instead of
for catalyst reactions, what participating in the reaction are only the atoms at the surface.
Okay.
So if you are using inorganic catalysts, such as some rare metal have excellent catalyst applications, or noble metals, but it's only the noble metal atoms which are on the surface participate in the reactions, and a lot of rare earths or noble metals inside the particles, they won't actually participate in the reactions or catalyst reactions. I won't say it's kind of a waste, but it is like they are not really contribute to the whole catalyst reactions. So people have been trying to different ways to change that. From that consideration, it actually makes the frameworks actually ideal for catalyst reactions, because you have large voids, you can blow all your gases or liquid in, and you have one metal at the node which can enable this kind of catalyst reactions. Now all the metals can participate, and all the metals are surrounding with enough number of the reactant molecules. That's a good part, and that's what makes this kind of frames so promising. Even they collapse sometimes, but it's still pretty promising for catalyst reactions.
Okay, thank you. Just to build up on that question, in the future, do you have any plans to investigate making structures that are more robust towards oxidation, maybe as a way to maybe end up with structures more useful for catalysis that can handle recycling better? Is that something that you might be looking into in the future?
Yes, that's a good question also, and a suggestion. Yes, in the future we are aiming for different applications, from catalysts to energy storage applications, such as electrical conduction for morphs are also really promising and interesting for people in the battery field, and also some applications such as the drug delivery. We are still going to do some work in the gas separation and storage applications, but we are expanding with focus on catalysts and energy storage. Yeah, that's our actually main targets in the future.
Okay, that's great. So next question, do you have a supporting slide that you can show us the methodology for transforming your structures into graphs? Because I know you described the method in your paper. Do you have a supporting slide or any graph that you can show us the process?
It's actually let me see. I'm not very sure. Maybe this one. Maybe this one can give you some idea of what we are doing. Like you start with morph 117. You can breaking the structure at all the connection points, and you can identify its framework, its backbones of the structure, and you can decompose it into, you see the linkers we have here, and we have the nodes here, and we have the way for them to self-assembled, which is the topology here. It's just one simple way to understanding how we proceed the whole representation or identification procedure. And yeah, I mean, that's basically it. And we tried both smells and selfies to represent the linkers. It's basically a molecular representation question or problem. And we found like selfies gives us like a highest validation score, so I stay with selfies for our as a part of our framework representation code.
Okay, so for my better understanding, you're storing all this information in a specific type of object, or are they stored separately when you're feeding them into your model?
They are stayed together. And we have different components to deal with different parts of the so-called RF code in the original encoder.
Next question. You mentioned that your SMVAE is jointly trained for property prediction, but your property data dimension or size-wise is different than your structured data set.
Yes.
Would it be possible for you to explain how you ended up finding a solution to that problem?
Yeah, we are using this kind of so-called semi-supervised method, or the so-called mask function. Using a mask function is like you can imagine without properties, your Latin space is well-defined points, collection of points without any color. They are all in gray or black color without properties. Well, after property training, they are gathering together to be the Latin space, and you can understanding the properties as adding colors to all the points in the Latin space. So now we were not able to finding all colors for the points in the Latin space because we have a huge training pool, about 2 million. So what we did is like we take random points in the Latin space and then calculate their properties. So basically, we have a very coarse dyeing process for the points in the Latin space. So we are still going to get the still going to get the the gradient, the color gradient, or the property gradient of the Latin space. It's just not as dense as it is supposed to be because it's so large. So we are still going to know what's the general trend of the general trend, or what's the general distribution of properties in the Latin space. We are still going to know which part of the Latin space may have better properties, which part of the latent space may not have, we may have a lower chance to have better properties. So we are still capable to following certain curve to achieve to chase gradient and to achieve like latent space points with better properties. And that's what we did to without calculating everything all, or without to measure array systems in the latent space to make useful predictions.
Okay, so just to build up on that question, have you tested if your model can do predictions with molecules it has not been trained on, but properties of, so that you can check if this process is working?
Oh yeah. Actually, I can show you some further figures here. You can see it's the latent space of the supermolecular version of autoencoder, which trained without the properties. When we trained it, we didn't include in the properties, but we still turned it on when we make the figures. You can see they are like evenly like mixed with each other in the latent space for all the sample systems for different applications. And if you turn them on, you can see that would be remarkable or obvious trend and clusters in the chemical space, such as here for the carbon dioxide uptake, which we take as an example in the presentation. You can see we have a clear trend, like in certain part of the latent space, you may have higher properties, and for certain part of the latent space, you have lower chance to have higher properties. Then you can start with sampling points in the latent space and search for points in the latent space for improved properties.
Okay, so
just to follow up on. Oh,
yeah,
go ahead.
Go ahead, Shahrzad.
Just to follow up on this question, how many properties can you optimize at the same time?
Actually, there is no limitation. We tried from 1 to 20, and the version of the encoder gonna take longer to be trained, but they still finished the job. They still were able to find the trend in the latent space when they joined the trend with both systems and properties. We didn't try even bigger though. Maybe, yeah.
Okay, and also a question regarding one of the previous sections that you talked about. So you're talking about data augmentation using computational calculations.
Yeah.
But at the same time, we know that so one of the way that the whole motivation for using like graph generative model is to reduce the cost of computation that you could do through computational modeling. But at the same time, you're using this to generate some data to be able to train your model on that.
Yes.
Have you been able to find a good balance that at the same time reduce the cost of computation, but be able to search a larger space?
Yes. So that's actually the tough question, and actually the first challenge we have to face when we're trying to building the training pool. Because for building any kind of deep general models, you need to have a larger, pretty large training set. Usually it's on the level of 10 to the 6 or on the millions of system level. So now we only have several thousand morph structures people has been synthesized. So what we have to do, we have to come out one way to sort of augment the training pool, but without adding something crazy or adding something not practical to be synthesized as frameworks. So what we do is like we start with all the linkers we were able to identify from the database, and what we do is like we do random functionalizations. In terms of that, when people are trying to synthesize morph, after synthesize, usually they do a further or the post-synthesize procedure, the adding functional groups to the structure or to the frameworks. That's what they do to either modify the properties of the frameworks or adding some better properties to the frameworks. So what we do is like we start with those kind of database, and we adding functional groups to the linkers like randomly at the random points. That's what we do here. For this linker, we can adding like different types of framework, different types of functional groups. And by doing that, we were at the end we were able to have like around 300,000 new linkers. And that's why when we put them together to building new frameworks, we would have a much larger training pool, around 2 million new morph structures. And that's what we do to augment the data set. And that's actually the only viable way people can actually figure out to realize this kind of augmentation without adding unnecessary complex like a chemical information to the training process.
Could you also a bit explain on what stage is your validation part in terms of validating that this structure that you have come up has a superior properties?
Yeah, that's a great question. Like this project is mainly finished before the COVID, and we have very strong collaborators in Northwestern and in Argonne, like Professor Randesner and Professor Omar Farha. They are already trying to start to test some of them. I think there comes COVID and the labs are shut down, so yeah, we have no progress after that. Now they are trying to restart their lab, but they have been shut down for several months. They have many more urgent stuff to do, so I guess it's getting postponed once again, and I hope they could start much sooner, but it just won't happen.
Yeah. Sure. Rouzbeh, is there any question that you want to ask?
Yeah, sure. So to go back to your data augmentation, I know one of the things you do, you randomize the linkers, if I understood correctly.
Yes, randomize the adding functional groups to the linkers.
Oh, yes. So my question is, for the ones that you have properties of, do you do augmentation also? And if that's the case, do you recalculate the properties?
No, actually, it's before we calculate the properties. You can see the procedure here I showed. Yeah, you can see it's very first step of when we start building a training pool. Is like we start to all the original structures, and we decompose to their like building blocks, and we do data augmentation, and then we have the 2 million morphs, right? And then we random selecting like 50,000 morph structures from those 2 million morph structures with random added functional groups to calculate their properties. That's our problem. That's our starting point. So yeah, they are already with the functional groups in the structures.
Okay, got it. In your paper, you mentioned you're using cyclical annealing scheduler to mitigate KL vanishing. Could you explain what KL vanishing problem is?
Yeah, actually, it's pretty complex question, because if you are working with the versional autoencoder a lot, you can see some versional autoencoders have trouble to be trained in a meaningful period of time, and some versional autoencoder may learn to trick you when they were trained, which means they are not actually learning anything, but they just learn how to trick you, and that's something we don't want. So we use the so-called so-called regulars, and people have been tested it for many different version of autoencoders. It's pretty effective, and actually I would recommend all the people who are working with deep learning models work with that kind of regular, and it's pretty useful, and it would make your training much faster, much reliable.
Okay. So my next question is regarding slide number 16. I think that's the architecture that you have. And I just wanted to know how the training process works. If you can just explain that, that would be great.
Yeah, this part is basically the decomposition part, or the identification part. You have one structure, you turn it into RF code. And when you have the RF code, you would pass all the one-hot encoded part to one component of the original encoder, or one of the encoders in the whole supramolecular version of encoder. And then you would pass the chemical meaningful selfies into another neural networks or another part of the encoders. And then you would encode them separately, and you would combine them into the same latent space. And then you would decompose them into different, convert them back into different, either one-hot encodes or different molecules. And at the same time, you can do property predictions, you can do joint training. And that's how the whole system is designed, and that's how the system works. And you can, every part of this kind of autoencoder can be turned on or off. You can only train on the linkers, and only train to predict the new linkers or new molecules. And you can also only train them based on their morph informations, because you want to have validated morph. You don't really need to predict like a new linkers. You can do that too. And you can also combine them to property predictions. Now you're kind of going through the chemical space of the 2 million morphs without explore any other new morph structures. So it's pretty versatile and flexible platform, which can be applied to different applications and with different load. And as the last part, it's the reconstruction part. With the new RF codes, you can convert them back to be frameworks and to be 3D crystalline structures with property calculate or predict, and then you can test it or validate in the lab.
So when you're sampling from your latent space, usually people report on the validity of the structures that they get. Have you observed the structures that are invalid?
Actually, when we do the predictions here, firstly there are two parts in answering that question. Firstly, there would be a very low chance to have like invalid morph structures, because we have very detailed. People has been worrying like maybe some kind of linker won't go together with some type of nodes. They cannot connect with each other to certain types of topology. So what we do is like we have some further decomposition for multiple connection linkers, such as here what I showed here, which have 3 connections. We actually have a further decomposition for them to be one organic node here and edges. By doing that, there would be very low chance for us to find the linkers without correct symmetries. People may worrying like maybe you predicting one linker with super long in one branches and super short in another branches. Maybe they won't put together to be real morphs. And we get around of that by decomposing it into further fund building blocks. that's also another strength actually for the ARF code, is like we avoid those kind of geometry incapabilities. And
Okay,
then that's one part of the question. Yes, another part of the question is like we have a morph validator here when we reconstruct the morph structures. If certain types of linkers simply won't go with certain types of nodes, we would exclude them. So our predict morph structure would be validated morph structures, geometrically validated structures.
Okay, so another question is about your graph, because I noticed you mentioned you're using smiles also.
Yes.
Would it be possible for you to explain which part of the data is in graph format and which part of it is in smiles format, and whether or not combining the two creates any complications?
No, we tried both smiles and selfies to represent the chemical meaning for linkers of the RF code, but we didn't really use them here in the final results, because we found out that the accuracy for predicting new linkers using selfies are much lower than selfies. So we actually only work with selfies when we're generating new morph structures, and we stop testing, smells in the final procedure of this project.
Okay, because one of the slides you just showed mentioned smiles for linkers. Could you explain what that means? Because I'm not sure I understand that part. That you were doing the process for creating, decomposing your structure. I think it was that slide. I don't know the number exactly.
Here, maybe?
No, it was the slide that you showed us when I asked for the procedure of creating a graph from each of the structures.
Which one? You mean this one? Or?
Yes. So you have a molecule, and you're representing that with smiles. Now, that creates a confusion for me as to whether or not you have used smiles at any point in.
No, I didn't.
Okay.
Here is just one example. As one example, you can actually include them into a screen. Yeah.
Okay. So my last question is whether or not you trained your components of your architecture all at the same time or separately.
Yeah, we start with train them separately. That's for sure, to test them, to make sure each of them work. And when we do the real run to optimize, to predict new frameworks and to optimize for frameworks with improved properties, we train them at the same time.
Okay, thank you.
No problem.
Thank you for the great talk. So just to summarize what we were talking today, so you showed that how using with graph models to represent the molecules, you will be able to search a larger design space, and you use generative model to discover new structures and applied your property, the favorite property that you want to look for. Here for MOF, you were looking for CO2 separation to be able to optimize your properties and structures based on that. Thank you very much again for your time and the great talk. We will hope to see you again in next events.
Yeah, thank you so much, guys. It's a very pleasure, to talk to you guys and to present here. Thank you, guys.
Same. Thank you.
Talk to you guys.
Bye.
Yeah. Bye.